Good afternoon. My name is Adela Lemus from Instituto Politécnico Nacional in Mexico City. It is my honor to present in this forum our study about the excellent capacitance of electrodes made from bituminous carbon. Electrochemical double-layer capacitors or supercapacitors are devices that store energy through charge separation on the surface of the charged electrode from resorption of electrolytic ions. Currently, there is a great interest in the development of supercapacitors in mobile applications, which meet the standards of efficiency, safety, low cost, and that are friendly to the environment. Activated carbons comply with these standards, and also they present thermal stability, chemical resistance, mesoporosity, and electrical conductivity, which are properties of activated carbons that make them attractive for charge storage processes. Here we present the structural and surface modification of bituminous carbon via a simple activation process with potassium hydroxide. Bituminous carbon is an abundant and little studied material for energy storage applications that could act as a material with added value. For the preparation of activated carbons, the bituminous carbon was ground using a planetary ball mill. The carbon product was sifted with diameters between 0.25 and 0.42 millimeters. The carbon was treated with a solution of chlorhydric acid for 6 hours at room temperature with stirring. Subsequently, it was washed with the ionized water until a pH of 7. After that, the material was dried at 120 degrees. Thermal treatment conditions for eliminating impurities and activating the raw material were established within a thermal range from 25 to 1000 degrees in nitrogen atmosphere with a flow rate of 20 cubic centimeters per minute. Potassium hydroxide and bituminous carbon were mixed at a mass ratios of 1:1, 2:1, and 3:1. Activation was carried out with these conditions. Then activated carbons were neutralized with a solution of chlorhydric acid during 24 hours. And finally, samples were dried in an oven and at 110 degrees for 12 hours. The label of the samples contains the mass ratio used for the preparation. Now let's see the characterization of these samples. The diffraction patterns of the samples show amorphous characteristics. The most intense peak at 25 corresponds to the distance between layers. The less intense peak at approximately 43 degrees to theta degrees corresponds to the carbon-carbon distance. Changes in powder X-ray diffraction patterns are due to the oxidation reactions that take place in the basal and the graphitic prismatic planes. They are more evident in this first one peak. The impact of the activation process on the gradual development of the porous structure is observed in some images in this slide. We can observe the increase in the mesoporous surface is proportional to the potassium hydroxide impregnation ratio. Nitrogen isotherms reveal differences in material textural parameters. In this slide, we can see isothermal curves type 2, like this one, for all carbons. The initial part of the curves corresponds to the completion of monolayer coverage. The values above 0.3 relative pressure are associated with the multilayer absorption that takes place in the mesopores. From 0.9 relative pressure The observed absorption, this last one, is evidence of the existence of macropores. In each curve, approximately 60% of the nitrogen uptake, total nitrogen uptake, was attributed to the presence of micropores and narrow mesopores. In the figure at the right, we can appreciate the pore size distribution that was calculated using Pygap's software. The intrinsic microporosity of bituminous carbon became mesoporous by the potassium hydroxide reaction. In this slide, we have the comparison of the information that isotherms provide. Please note, first of all, that we are here reporting pore surface values that exceed 700 square meters per gram. Those that are made with non-flat sheets, typical of non-graphite structures, and whose interplanar spaces are between 0.2 and 2 nanometers. Now let's talk about porosity. In activated carbon 11, we can see that microporosity decreases and mesoporosity increases relative to the original bituminous carbon. In the case of activated carbon 21, both micro and mesoporosity increases, triplicating the initial mesoporosity of bituminous carbon. And for the third one sample, the structure combines a greater volume of mesopores at the expense of having the lowest volume of micropores owing to the action of potassium hydroxide. Besides, the total volume pore clearly increases with the activation methodology proposed. In this slide, we can see the XPS high resolution spectra of carbon 1s of the four materials, which let us appreciate the presence of several functional groups that are quantified in this table. We can see that the carbon-carbon defects grow in a general trend, grow with the amount of potassium hydroxide used. The carbon-carbon bond is the most abundant species in all the materials, except for the most oxidized one. And the oxygenated groups population of the materials increases proportionally with the amount of potassium hydroxide used in thermal treatment. It is worth to notice that activated carbon 31 material exceeds almost twice the amount of oxygenated functional groups relative to the two first samples. The cyclic voltammogram curves of the carbon materials at different scanning speeds are shown in this slide. From them, we can understand that the presence of oxygenated functional groups increase the wettability of the electrode surface and improve electronic conductivity. With increasing sweep speed, the current densities increased, and simultaneously, the CV curves gradually slanted, which is related, this phenomenon, to the fast migration of ions between the electrolyte bulk and the double layer in the electrode. In this slide, we compare the performance of Bituminous carbon, the original one, at different scan rates, with similar works reported in the literature. These results demonstrate that the excellent electrochemical characteristic of the electrodes that we are here reporting. In the figure at the left, we observe the specific capacitance values plotted as a function of voltage sweep rate. The high capacitance values at the current density values demonstrated the rapid diffusion of ions in the electrolyte solution. In the figure at the right, we have the values of the specific capacitance as a function of the current density. The best value of specific capacitance corresponds to the activated carbon 31, which shows an augmented capacity of 46% regarding bituminous carbon. Slightly distorted galvanostatic charge discharge curves are shown for the cells of the activated carbons in this figure. The different impregnations ratio had, in general, the effect of decreasing the slope of the charge-discharge curves, which results in an extension of the total charge-discharge time. And the specific capacitance retention of the activated carbon's electrodes after 10 charge-discharge cycles is approximately 93%. Here we have the Nyquist diagrams of the sample studied, where the real and imaginary parts are given in ohms to determine the capacitive and resistive contribution of the electrodes. The Nyquist plots were adjusted and analyzed based on the equivalent electrical circuit model using the ZetaView program. So we have these 5 contributions to the capacitance, and among all of them, I highlight the parallel double layer capacitance, which is an amount that improved as a direct effect of the user activation methodology. Finally, we arrive to the following conclusions. Bituminous carbon performance as an electrical capacitor is comparable to that of other carbon sources. The obtained materials showed values of capacitance superior to that reported for vulcan carbon, and here we have the values determined for each one, being the best value for the activated carbon 31. The best materials features are the following: bed surface of 1,180 square meters per gram, micropore volume of 0.15 cubic centimeters per gram, and mesopore macropore volume of 0.72 cubic centimeters per gram, several oxygenated functional groups, along with the lowest resistivity to ionic transport obtained from electrical equivalent circuit model. This is all, and I want to thank you for your attention and the kind invitation to the participation in this forum.